Okay, in this video, we're going to solve a system of differential equations, and we're going to get a repeated root. So we're going to go through the process of how to get that second solution that you need. So we have our system here. It's already written in matrix form. So vector x prime equals matrix 1, 4, negative 4, 7 times x. And we also have an initial value. X of 0 equals the vector negative 2, 1. And we're going to find the eigenvalues first. So determinant of a minus lambda I, that means we're going to subtract lambda from the main diagonal and find the determinant. So we multiply the main diagonal, 1 minus lambda, negative 7 minus lambda, subtract the other diagonal, so it'll be plus 16. And we'll just simplify here. Negative 7 minus lambda plus 7 lambda plus lambda squared plus 16. And then simplify again. We get plus 6 lambda and then plus 9. So that's a perfect square. That's lambda plus 3 squared. So that gives us lambda equals negative 3 with multiplicity 2. All right. So we still need to find the eigenvectors for lambda equals negative 3. So we need to solve this equation. A minus negative 3i times x equals 0. So it'd be a plus 3i. So I need to add 3 to the main diagonal. And then augment with 0 and row reduce. So I get 4, 4, and then negative 4, 4. This is going to be easier row reduce, right? So subtract the second row and the first row. We get zeros on the bottom. And then divide the first row by 4. We get 1, negative 1, 0. So I've got my leading 1. I've got a free variable. So x2 is free. And x1, if I solve this first equation for x1, I get it's equal to x2. So my eigenvector here is 1, 1. All right, so we need two linearly independent vectors to make our solution. And, since we only have the one eigenvector, we've got to come up with something else. So here's what you do. You're going to take this same matrix. You're going to augment. Instead of augmenting with 0, you're going to augment with your eigenvector that you just found. When we row reduce this, again, this is easy. We're going to get row zeros on the bottom because they're the same row, and then divide the first row by 4. So I get 1, negative 1, and 1/4. All right, so same thing. We've got leading 1, top left corner, got a free variable here, x2. So x2 is free. So x1 is x2 plus 1/4 now, okay? And, the only thing you have to worry about when you're plugging in your free variables is you can't plug in your free variable and get a 0 vector, right? You don't want your eigenvectors to be 0 vectors. You don't want this vector to be a 0 vector. But because of this 1/4 here, I could plug in 0 for x2 and get a non-zero vector. So if I do that, then the vector would be 1/4 and 0. All right, so now when we write our solution, so our general solution, we're going to say, C1 e to the negative 3t times the first eigenvector. So that's normal, what we usually do, okay? And then the other solution is going to be C2, and then you're going to have a sum. So you're going to have t e to the negative 3t. Remember when we did repeated roots earlier, you had to multiply by t. So this is kind of related to that. And you're going to use the same eigenvector. And then you're also going to add e to the negative 3t times this new vector. Okay. And, you could simplify all this. You could put it all together. I'm going to go ahead and solve for the constants because we have an initial value. So let's do that now, and then we'll worry about putting it all together. So the initial vector is negative 2, 1. So we should get negative 2, 1 if we plug in 0 for t. You plug in 0 for t in these, e to the negative 3t's, that'll give us e to the 0, which will be 1. So for this first one, I just get c1 times the vector 1, 1. And for the other one, when I plug in 0 for just t in front of the e to the negative 3t, that's going to knock out this entire vector here. So that's going to be 0 times this thing. So we can drop that one. And then for the second half here, we've got e to the 0t, or sorry, e to the negative 3 times 0. So that's e to the 0. It's going to be 1. So I get 1/4 0. So this is a system that I can solve pretty easily. Coefficient matrix. And then we augment with a negative 2, 1. And let's see here. I could use this this 1 to eliminate this 1, and then switch the rows. So if I just take row 1 here and subtract row 2, and then switch the rows, what do I get? So 1 minus 1 is 0. 1/4 minus 0 would be 1/4. The negative 2 minus 1 would be negative 3. And then I'm going to multiply the second row by 4. So negative 3 times 4 would be negative 12. So I get C1 is 1 and C2 is negative 12. Right? So now I can plug that back into my solution that I just wrote down. So C1 is 1 and C2 is 12. So X would be 1 times e to the negative 3t times that eigenvector 1, 1, and then negative 12 times this this big vector t e to the negative 3t times 1, 1 plus e to the negative 3t times the vector 1/4 and 0. So now I think it does make sense to try to put all this together into something that makes a little bit more sense. We can simplify this a little bit. So let's just worry about the second part. So let's multiply the negative 12 throughout. So that'll give me negative 12 inside this vector, and then negative 12 times this vector. So negative 12 times 1/4, that would be negative 3, and then 0. Right, and then we could say factor out the e to the negative 3t and then add the rest, right? So I've got negative 12t, then I've got 1 minus 3, that'd be negative 2. And then the second one, I've got negative 12t, and then I got 1 plus 0. So just be plus 1. So that looks a lot better there, right? So, you could go further, right? You could multiply the e negative 3t inside. So you'd get negative 2 e to the negative 3t minus 12t e to the negative 3t. So that kind of looks like a solution that we would have gotten when we were just solving differential equations and not systems, right? So that would be the solution to the first equation in my system, or the first function in my system. And then on the second one, they get e to the negative 3t minus 12t, e to the negative 3t. You can think about this x as having, say, two functions, right? F and g, or x and y, right? It's got two functions that you're trying to solve for. So these would be the two solutions that satisfy the system. But I kind of like this one the best. All right, hope this helps.